All right, welcome to today's webinar organized by the European Membrane Society. Our speaker today is Professor Soraya Malinga. So Professor Soraya obtained her master and PhD degrees from the University of Johannesburg, and she's an associate professor and co-director for the Joint Research Center for Water, Environmental Science and Technology at the same university. The focus of her research is on membrane science and water purification. She's a board member for the African Membrane Society, and she was honored for her research as a runner-up under the Distinguished Young Women Researchers category by the South African Women in Science Awards. Professor Soraya was recently named as a National Science and Technology Forum Awards finalist. Now she will share her knowledge on dendritic polymer integrated nanostructured membranes for water purification. So the stage is yours, Soraya.
Thank you very much. And it's a great pleasure to come and share insights of my work. So I will be giving an overview of the work that I've done for the past 10 years whilst I have been in research. As Georgie has introduced me, I will just give an overview of the work we've done on dendritic polymer integrated nanostructured membranes for water remediation. Since my main focus is on water remediation, I will present most importantly work on removal of organic, inorganic pollutants and bacteria from water. And having to highlight that membranes are not only limited in this field, but they are used as well in energy and in industries such as beverage and food industry. Advantages of using this technology is that membranes are quite flexible and their properties can be adjusted to suit that particular application that you're looking for. And they're quite effective materials for the high rejection of your targeted contaminants. They are also a technology that can be used in a hybrid process. So for instance, in a water treatment plant, normally they are used as a polishing step. However, membranes are prone to fouling, and this then has a direct effect on the membrane lifetime. In our research, we have looked at the possible use of what we call nanostructured membranes, where we have used material science and matched it with nanotechnology to try and improve and fine-tune structures in membranes such as the mechanical, chemical, thermostability, charge density, porosity, and hydrophilicity. And these properties have a direct effect on the functionalities in that they introduce functionalities such as adsorption, photocatalytic properties, catalytic properties, and antimicrobial properties. As we all know that we currently have challenges in the use of nanofillers in membranes, such as poor dispersion of the nanomaterial within the polymer matrix, aggregation of these nanomaterial within the membrane matrix, which are also disadvantaged as well by the weak chemical interactions between the nanomaterial and membranes, and this leads to non-compatibility and obviously leaching out of the nanomaterials. We have looked at different types of fabrication, phase invasion process, where we basically have your polymer and nanofiller, and your solvent. This is combined together to form a casting solution, which can be cast on your membrane. And via phase invasion, you could get your flat sheet membrane. We've also explored the use of recently moving towards hollow fiber membranes, where we would have a different setup from the flat sheet fabrication, where we have a polymer solution and a bore fluid going through a spirit, and we have our membranes converted to a hollow fiber. These different types of membranes are quite better than the full flat sheet, because we can now look at scaling up our technology. We've also used interfacial polymerization, where we have formed a very thin film active layer on the membrane using a commercial membrane as our support. We have used, in our case, since my research is more geared towards the use of hyperbranch polymers. So for the amine terminated, where you would use MDPI, we would use a hyperbranched polymer, which also has NH2 functionalities. And with its reaction with your trimethyl chloride at the interface, it will form a very thin film. So what we have done, we have included different as well nanomaterials in this thin film in order to enhance properties such as hydrophilicity, have enhanced separation, as well as enhanced performance in terms of flux. We've also explored another fabrication process, which was taken from a study by Diallo, I think in the early 2000s, where we have attached a commercial membrane on the rotating drum. So we are not just spinning fibers on a foil like you would traditionally prepare nanofibers, preparing mats. But in this case, we have a commercial membrane rotating on the drum collector, and we prepare the nanofiller and the polymer solution, which is inserted in the syringe, and we electrospin on the commercial membrane. This process requires, though, a lot of optimization, such as your collector distance, your polymer percentage, so that you can get ultra fine nanofiber membranes. So the main focus of my presentation today is we embarked on using this quite big molecule, which is hyperbranch polyethylene imine, because, as I had mentioned, it has NH2 groups on its periphery, which are quite abundant. And these NH2 groups really assist in improving the hydrophilicity of the membranes. And we have also used it to attach other molecules, such as multi-wall carbon nanotubes, as well as enzymes on this hyperbranch polymer, because we're taking advantage of the NH2 groups, which are quite easy to functionalize. We also have internal imines within the structure that can act as chelating ligands, because, as I mentioned before, we are interested in preparing also nanoparticles that can have catalytic and photocatalytic properties induced within the membrane. What these imines do is that they can chelate the metals that you're trying to reduce to nanoparticles. They can also chelate. If you are interested in removing heavy metals from water, they're also an added advantage. Now, when we come to the structure of a hyperbranch polymer, although my structure doesn't look globular, the structure does sort of like provides a shell or like a protection or cover to the nanoparticles that you are preparing, such that it sort of controls the shape and size of your nanoparticle. And we know that in nanomaterial synthesis, that is important because size, shape obviously coincide with the activity of the nanomaterial that you are trying to prepare. The last property that we take advantage of is that this material has nanocavities or holes within it that are hydrophobic. So it's a quite a tricky, not a tricky, but it's a hydrophobic material inside and hydrophilic material outside. So it gives you both properties and you can use them to your advantage in that it can act, as I said, within those cavities. We have these internal imines that can chelate your particles. Then you'll be able to have your catalytic sites as well as adsorption sites within a concentrated area, and you can have maximum photodegradation or catalytic degradation of your targeted molecule. I think I have summed up the slide in the latter one. We have then explored the use of this hyperbranch to improve hydrophilicity, flux catalytic, where we've prepared catalytic particles, as you'll see in the next slides. We've used it to improve the removal of organic pollutants and heavy metals. Also to prepare photocatalytic nanoparticle, we've grafted different molecules such as multi-walled carbon nanotubes, enzymes, nanofibrous membranes, and also we've prepared biocidal particles such as your silver and selenium that are targeted for removal of bacteria. So in the last slide, I will just focus. I've tried to group the different types of membranes. I have not included all my work, but I've tried to group it in such a way that there is flow. So we have prepared catalytic membranes for removal of chlorinated organic compounds. We using thin film preparation method, where we embedded iron and palladium within the thin film, which was sandwiched between the bottom layer, which is green, and the top layer. Then the bimetallic coexisted, hopefully inside that very thin film layer. We use different characterization techniques such as AFM, TEM, before we actually embedded the iron palladium material, because membranes are quite difficult to sort of investigate your nanomaterial that's obviously within the thin film. So we looked at SEM-Fib. So SEM-Fib has a laser that you can use to sort of like slice off the top of your membrane very slightly without destroying, obviously, the membrane. So we could really see if the thin film consisted of the iron and palladium. And we did some EDS analysis. We could see that it is nicely spread within that area. And our EDS analysis also showed when we increased the HPI, obviously, we saw that this had a drastic effect on the surface roughness of our membrane. For the final application, we targeted PCB 153. Our LCMS studies did show that we have degraded it into other compounds, which was PCB 52 and PCB 2. So we were successful in the dechlorination of this targeted compound. We then also further used the hyperbranched in first preparing another bimetallic system, iron and copper, in a multi-walled carbon nanotube. So what we first did was functionalize the multi-walled carbon nanotube with carboxylic acid so that we could be able to link it with the NH2 groups of the hyperbranch polymer. Then we prepared the iron copper bimetallic within this composite. So it was a composite. Then we embedded it via the phase invasion method on a membrane. So hence I have indicated that the properties we were looking for from the hyperbranched was prevention of agglomeration, the presence of cavities, and the fact that they can induce hydrophilic properties on our membranes. So we did a wide array of analysis, which was AFM, TEM as well, proved that the iron and copper coexisted with the multi-walled carbon nanotube. Then we exposed it as well to 2,460 CP for removal. We found that for these membranes, we had enhanced water flux and improved antifouling properties when we exposed them to BSA protein. Leaching is also a concern as well when we do nanofillers in membrane. So reviewers will always ask if the material that you've embedded does leach. So in most of our studies, we did some leaching analysis where when we collected the permeate, we could analyze it for the presence of that particular metal that we embedded. So in this case, we looked at iron and copper. Although we do not have sort of like a guideline what to compare with, so we would compare it with we have South African national standards to look at what are the acceptable levels of iron and copper in water. So we found that these were quite low, but other people will be interested in toxicity, but that will be further investigated because then there we need toxicologists to see if these materials have an effect to particular cells that they can be exposed to. We've also looked at photocatalytic membrane for the removal of pharmaceutical. In the early years of our study, we looked at targeting triclosan, which is a pharmaceutical that is as known, and we exposed it to bismuth vanadate, which is a photocatalyst. We observed that when we prepared bismuth vanadate within the HPI now, we could see two phases. Initially, we had a monoclinic phase, but as we added the HPI, the tetragonal phase was shown. And this was an added advantage to us because when you read in literature, this increases the activity of your nanomaterial. We also found improved flux and hydrophilicity upon addition of the fillers, and the membranes were quite effective in the removal of the targeted pollutant. In our latest work, we also targeted another pharmaceutical. We looked at a tetracycline and a heterostructure in this case where we looked at graphitic and niobium oxide. So we found, because we first prepare the niobium on its own in using HPI as the dispersant or the host, we found that we could get quite very small diameter nanoparticles that coexisted with the support, which was graphitic in this part. Graphitic is very useful as well as a nanofiller because it has its own photocatalytic activity. But if you combine it with another photocatalytic material, it even gets more enhanced if you form a heterostructure. It is also hydrophilic in its own because it has NH2 groups. It is also antibacterial as well. So it was a good choice of support as well. We also found enhanced hydrophilicity, water intake capacity, and pure water flux, which was accompanied by enhanced photodegradation and byproducts of tetracycline. We've also explored the use, as I said, the HPI has those numerous amine groups on its periphery. So in a way, we are able to attach, so I've shown a slide where we've attached multi-wall carbon nanotubes, which are quite big molecules. We also demonstrate in this slide attachment of enzymes, which then induce biocatalytic activity. This was quite interesting work because it was my first time working on something out of my field, more biology based. So what we did here, we chose to, as I showed in the last few slides, where I said we spin the fibers on a commercial membrane. So that was the first thing we did. Then we use a linker, glutaraldehyde, to attach the lacase. So you can imagine the lacase dangling, grafted on the fibers, which are also attached on the membrane as a support. So why we sort of went the nanofiber route is that nanofibers are known for porosity enhancement. They are known for high enzyme loading capacity. The HPI, in a way, we wanted to ensure that we have maximum loading of the enzyme because of the numerous amine groups. They also assisted in the fact that they would induce hydrophilicity. Also, literature does state that if you have a hydrophilic component in your enzymes, it does prevent aggregation. The architecture, the globular structure that I mentioned before, can also allow uniform dispersion and free movement, because enzymes need that free movement to the substrate or the targeted pollutant or substrate that you are trying to target or remove. And because they have numerous branches as well, as you can see in this diagram that we tried modeling, they can act as spacer arms to restrict the binding of the enzyme so that they are not restricted and they are able to be active and achieve their purpose. So with more research, because we did not know how we could detect a biological component on a membrane, obviously we can't use SEM. SEM we could use because lacase have that copper center. That's what makes them quite catalytic, biocatalytic, because they have a copper center. Depending on the type of strain or where you have extracted your lacase, they can have up to 4 or 6 copper centers. So because we wanted something similar to EDS and we couldn't use SEM, so we used what is called correlative light electron microscopy, just to see if, yes, we can see those lumps or those aggregated secular particles on our fibers, but wanted to see if this was indeed an enzyme. So we went to seek analysis, CLEM analysis. What you do is that you soak your membrane in a dye. So this dye, when it interacts with light in the microscope, it fluoresces to green. So I guess depending on what dye you have used. So we were able to see that they were nicely spread or dispersed within our membranes, and then we exposed them to bisphenol A, and we were able to get quite interesting results as well. Then for antibacterial properties, we've only explored silver and selenium. The same with silver, we opted to use nanofibrous membranes where we prepared the silver within the membrane. So it was an in situ kind of preparation. So we exposed, so in the casting or in our casting solution, as I showed in the other slide where we have our syringe. So we had our polymer of choice, PS, the solvent, and the silver. In this case, we use silver nitrate. So we spun that. A lot of optimization, as I said, in terms of controlling your size. So we did quite a lot of optimization that normally takes about 6 months. Then we expose the membrane to UV light to reduce the silver salt to silver 0. We also prepared these within hyper branched because obviously silver does aggregate. So it acted as a dispersing and capping agent. When we viewed this under the microscope, we could see that they're quite small and nicely dispersed, and the shape was sort of spheres. And we then exposed these to different microbial analysis. This work was done in conjunction with a colleague of mine who's an expert in microbiology. And we found that the presence of the silver assisted in inhibition attachment and biofilm formation of these bacteria on the surface of our membranes. If you look at the slides on the right, you can see A to C, that's the unmodified without the fibers and the active silver. D to E, then we could not detect any of those bacteria substrates on our membrane. Recent work, we have also used selenium, this time prepared in graphitic carbonitride. We used as phase invasion. What we got with our particles, these were they were not spheres but rods. We then exposed these as well to microbiology analysis where we did inhibition. So we would cut the membrane, put it on an agar plate that has the targeted bacteria. Then we measure the zones of inhibition. We could find that as we increase the concentration, the zone of inhibition became much more, which showed a positive result for the membranes. But with these membranes, I must say that we did quite have a reduction in flux. I'm still trying to figure out, but perhaps as well with the shape of the particles, it might happen that there might be blockage of the pores, or yes, that needs further investigation, because when we looked on the surface as well of our membranes on SEM, we could see that A and B, those are the unmodified. C and B, we can see that there's disruption of the actual bacteria, because you can see that there's sort of like the cell wall is disrupted, and there's no more bacteria that can be seen on the surface of the membrane. So in conclusion, we have used different fabrication processes, and we're still continuing with more work to improve properties of these nanostructured membranes. And we can safely say that dendritic polymers can be used to achieve uniform dispersion of this material, improve compatibility and interaction with nanomaterials, which are still challenges using nanofillers within polymer matrices. The outcomes as well, where we have seen improvement. I know there are other instances where we can't see improvement. We have seen enhanced hydrophilicity, water flux, antifouling properties, and improved separation. And the work does demonstrate that nanostructured membranes are a promising approach in terms of organic removal in pharmaceutical, textile, and agricultural industries. There are still major challenges though, because we still need to look at environmental toxicity, which then raise public health concerns of this nanomaterial, cost effectiveness of industrial scale membrane fabrication as well is still under debate. Where are we going to? We are looking at, but we're still working at very small scale, hollow fiber membrane. We've had collaborating partners. Special thanks to Dr. Ibenesh. I think when she trained us, she was still with Kaust in Saudi Arabia. Dr. Katie was my collaborator in India. We are still figuring out this, but we are very thankful for training from Dr. Abenesh, who's really assisted us with the students. And my current and students who have completed their work under my supervision. I wouldn't have done this without them, as they do all the digging. My collaborators, international, local, and industrial collaboration collaborators. Thank you very much. And to my funders, thank you for listening. I hope you have gained quite some insight of the work that we do in South Africa at the University of Johannesburg. If you have questions, I'll be able to answer them, or you can email me. The first slide does have my email address. Thank you.
Thank you, Soraya, for the nice presentation. So indeed, time for questions. Any question from the audience? You can either unmute yourself and then ask the question, or we have a chat where you can type in your question and I will read it. While we are waiting for the others, I actually have one question, so maybe I should the first question.
Okay.
So you were mentioning the removal of these chlorinated organic compounds. So I was just wondering about the perfluorinated substances, which are nowadays quite trendy and very important pollutants. So do you think that your membranes would work also for the fluorinated version of these pollutants, or what is the main difference between the two?
Okay. Yes, we are working. I started this year on working on PFAS. So you are right. We are looking at a biocatalytic membrane and a photocatalytic membrane as well. So yes, so it is work that is in the pipeline. And yes, because they have quite strong CF bonds, we'll just have to wait and see. But it is possible via photocatalytic degradation.
Okay, so you're working on these approaches.
Yes, yes.
Looking
Yeah.
forward to the outcomes. Okay.
Yes.
All right. Any
It's
questions?
it's still new work in South Africa. I think there are a few people who have detected it in water. I have started removing as well, but not using membrane technology.
Okay. We're checking the chat in the meantime, but
Okay.
no questions at the moment. Okay, I also have another question. So if nobody's asking questions, then I will go again. So what about the amount of these nanomaterials that you put inside? So what is their ratio or cost associated with the total cost, or relative to the total cost of your material?
Okay.
Do you think that you can bring that down? Is that practical, and so on? What are your thoughts on that?
So since we're working lab scale, we're still using, so the normal for phase invasion, it's 80% the solvent and 20% of the polymer. So we try and sort of change the amount of the polymer part. So we're still working with quite low values. We're still not at that stage where we need to upscale. Hence, I said the cost effectiveness as well is something that we need to really think about moving forward, to see how we can produce these in large scale, because they can be really pricey. So perhaps then we'll need to look at more natural ways. I know a lot of people have published, especially, I'm not sure if you've read some on metal organic framework. I know people are using green methods of preparing those. So perhaps we also need to look into, we are with the current student looking at the use of biodegradable polymers for preparation of our membranes. Yes. So to cut cost and as well, maybe scaling up will be better. Using perhaps, like local material that we can source.
Yeah, of course.
So those are the options.
Great, thank you. Okay, any questions? Okay, I don't see any questions in the chat.
It means was I very clear, or there was no one listening?
We can wait one more minute and then let's see.
Okay.
Okay, you can see the question, right?
Yes.
Okay, awesome.
Okay. The interaction. So in this research, we chemically bonded the both, because NH2 and COOH can interact, but under long reaction conditions with the addition of triethylamine. So we chemically bonded the two, so that when we reacted them, we had a new bond forming, which is an amide bond. So these were chemically combined. That's how we sort of like interlinked them. I don't know if I've answered your question. Can you give more details about the transport of PCB53 through the films? Where the films dense? Yes, I can say the films were dense, because as we added more of the HPI, we could measure that there's an increase in thickness, right? But how, because the PCB53 was now a byproduct of what we initially had. So what we thought the mechanism was in this case, remember I said in our thin film we have hyperbranch polyethylene imine, and we had the bimetallic system. So we assumed, although we haven't done transport studies, how we demonstrated it in the graphical abstract was that we have these, I don't know if I can quickly go back to the presentation slide, if I have the graphical abstract of that one. Oh, okay, I don't have it. But the main idea was that because the PCB 153 is hydrophobic, if it happens that it's captured within the membrane, it can be rejected. But if it does go through, of which maybe some of it did go through, when it's captured within that HPI structure, which supposedly have the iron and palladium, you will have that catalytic reaction, and you will have that degraded to the PCB 52. I don't know if I answered your question, although that would need perhaps modeling or further transport studies to indeed confirm the theory that we have. Okay, how can dendritic polymer membranes be needed to balance high selective permeability? A good question, because we are also trying to get the trade-off balance between high rejection, high permeability. So what we have done is that we are trying different formulations of the nanofillers that we are using. In that way, we also do the permeability of the membranes. We also measure the permeate flux. Depending really on the nanofilter that you put in, I've in my observation, with some nanofillers at high concentration, you have perfect rejection and perfect permeability. But in other instances, it just gives you the opposite. So really, I think it does require proper optimization as well. I really don't have the answer for now, because we are still trying to also get that balance in enhanced rejection and enhanced permeability. Thank you. Okay. Thanks, Lydietta. Thank you for listening. I think you asked me this question as well in Euromembrane in some conference. We did measure the activity of the lacase on its own, and after supporting it on the membrane, we found that the activity was still okay. The support did not tamper with the activity. We did not really have any model to test it, but we used enzyme substrate. So for lacase, we used cereal galdazine, which is a substrate for lacase. That's what we used to measure the activity. We also did stability studies. We kept our membranes, stored them away for like 30 days, so we could do the activity every other day to see if when we store them for a longer period of time, what happens. So we could confirm that as well, although it does reduce, but not so much. So we use the same substrate. Then we just use normal UV measurements as well. I hope I answered your question. We are also doing more work around enzyme. That was the only work that I published, but I'm working on more studies. Thank you very much for listening.
Okay, I think we have no more questions. So thank you very much, Soraya, for the nice presentation. And as you can see, it triggered a lot of questions and discussions.
Yes.
So that was very nice. So
Yes,
thank you very much again. And I'd like to remind everyone that the next webinar, EMS webinar, will be on the 8th of November. So watch this space. Thank you, everyone. Have a nice day.
Thank you very much for the invitation. Much appreciated.
Thank you. Take care.
Thank you. Thank you. Bye.